Good morning, ma'am.
Good morning. Is my screen is visible? Please respond. My screen is visible. You can type in the chat box also.
Mm.
You can type in the chat. Okay, okay. Let me remind. Okay, it is raining here, so let me remind if my screen and my cursor is not moving. 28 students. Okay, let's start the class. So earlier we discussed about a method of joints and method of section. Hope that part is clear. If it is still remain confusion, let me know. We'll take some extra class later on. Okay. So let's start with new topic: thin and thick cylinders. So basically, thick and thin cylinders you have seen in your day-to-day life. Okay. These are also called as pressure vessels. So a pressure vessels is used for storing liquids or under pressure. You can take an example of pipeline through which pressurized fluid flows is treated as pressure vessels. You have seen the pipelines, big pipelines, then LPG gas. Okay, then generally these thick and thin cylinders are generally termed as pressure vessels because the liquid and gas in that cylinder is it gives pressure to its walls. Okay, normally vessels are of cylindrical or spherical shape. So whatever means these thin cylinders are in cylindrical or spherical shape. If you go to some refinery or if you go to some company, they store gas or liquid in these kind of cylindrical or spherical shape. There are several examples of pressure vessels which are used for engineering purpose. They include boilers, gas storage tanks, metal tires, and pipelines. So these are the some typical examples. You can take the example of your day-to-day life. You use bottle. Okay, the what we store here liquid. So liquid gives the pressure on its walls. These are the pipelines you must have seen along roadside. They used to the sewage water is to flow from this pipeline. Sometimes these pipelines are used to pass the gas, these oils. These are the gas tankers, right? So these are the typical examples of thin and thick cylinders. So let's start with thin cylinders. Okay, so uh, uh, these cylinders are categorized into two basic parts. One is thin cylinder, another is thick cylinder. So when you consider that your cylinder is thin, when the thickness of the wall of the cylinder is less than 1/20th of the diameter of the cylinder, then the cylinder is considered as thin cylinder. That means, suppose I have a cylinder. Let me note with another color. Suppose I have a cylinder of this. My screen is visible, I guess. Please let me know, okay? If it is not visible. Suppose this is the cylinder. Okay. If its diameter, this will be your diameter, right? You can take an example of your normal pipe you use to sprinkle water in your garden, right? You used to wash your car, bike. So what happens when we open the well? Water comes in pressure and it flows out, right? So it will be considered as thin cylinder when its diameter, suppose this is the diameter, suppose you have a value of diameter. If you divide this value by 20 and this value is very greater than the thickness of the cylinder or thickness of the pipe is very less than d by 20. Suppose you have a diameter of 50. Okay, 50 if 50 mm, you have a diameter of 50 mm. If you divide that value with 20, you'll get some value. If that value is greater than your thickness of the pipe, then it will be considered as thin cylinder, and opposite of that you'll consider that your cylinder is thick cylinder. Okay, so when the thickness is very, I mean, that means you can say thickness is kind of negligible in this area. So whenever you get thickness very less than your d by 20 of the cylinder or pipe, then your cylinder is considered as thin cylinder. Otherwise, it will be considered as thick cylinder. So this is your upper surface. This is the diameter. This is the thickness, and these are P is the internal pressure acting on that cylinder. Suppose this is you can also take an example of your Diet Coke. It is in cylinder shape, right? So the liquid in that Diet Coke, see, you have a lid here. When you open, it gets sound. The pressure in this, the liquid which is applied, it gives pressure in this, it gets released, right? So this P is acting on its walls. So this P is acting on its walls. So this is your internal pressure. Due to this, this is your internal pressure, and this is your length of the cylinder, or it may be spherical. Then this is the diameter of the cylinder. So length of the cylinder I have considered as L, diameter is D as diameter of the cylinder, T is the thickness. It will be like this, right? Let me note once again. So this will be your thickness. This part will be your thickness T, and P is your internal pressure due to fluid or gas, because you use these cylinders to store your gas or liquid. So P will be the internal pressure. Now, due to this internal pressure, suppose as I've discussed earlier, that whatever the structure exists, engineering structures, we always design those structures, right? These cylindrical pipes, tanks, all are designed based on some value. There will be some design working value. There will be two value. One will be working value and another will be design value. You always, this thickness, this T thickness will depend on this design value. How will you know that how much thickness will be required for this purpose? Everyone has will be different thickness, right? Since for based on the purpose of use, you will design that structure and you will design that thickness of the cylinder. So you need to find a working value and design value. So you always have to work that your stress does not exceed the working stress. If it exceeds the working stress, it will reach to design stress, and after reaching the design stress, if the value gets more than that, then your this pipe will get burst out. This will not able to carry the pressure by this cylinder. This part is clear what I've discussed. I'm saying that when you design these cylinders, thick cylinders or thin cylinders, the main parameter is the thickness. Okay, based on this thickness you will design, and based on the purpose you will design different cylinders. Suppose for you are using a bottle. You need to design a bottle. The bottle doesn't need to carry much load. So based on that load calculation, you will design that bottle. Suppose you need to design a tank for a refinery. So you will design the thickness, that suppose that tank can carry 120 liters of liquid. So you have to design the tank in such way that it can carry 120 liter effectively. Suppose I have overloaded. I have filled the tank with uh, suppose I have filled the tank with 150 liter. So that will be overload or to not. So your cylinder won't be able to carry this load. So this is called design load. So that it can carry only 120 liter. It cannot carry 150 liter. So this will be your design value. Okay. So you have to design the structure based on your design value only. If you exceed that, it will get burst out. It won't be this cylinder won't be able to carry that load. So basically we will study what are the factors and how this cylinder can get failed. Suppose this is one cylinder I have. Okay, it will fail in two directions. One is longitudinal direction and one is transverse direction. Okay, when the pressure exceeds certain limit, your cylinder will fail. It can fail on because of only two reasons. Okay, because of two. One is transverse. That means when your cylinder gets, it will fail by two. By let me come to the another slide. We'll discuss. So generally cylinders, generally cylinders are emerging storing fluids. Cylinders are employed for transporting or storing fluids, that is liquids and gases. Examples are LPG cylinders, boilers, storage tank, etc. Okay. Due to fluid, due to fluids inside a cylinder, these are subjected to fluid pressure or internal pressure. Okay, these due to this fluid or gas inside a cylinder, these are subject to fluid pressure or internal pressure. Hence, at any point on the wall of the cylinder, the three types of stresses are developed in three perpendicular directions. Suppose this is your cylinder. Suppose it can fail. I said it can fail in two direction, major two direction. One is transverse. So when the pressure when it fails by transfer, that means it will make the cylinder into two half. This one will be one half. This one will be one half. Hope you are getting my point. That means this way. Screen is visible. That means it will get into two halves. This if it is getting failed by transverse direction, that means due to the longitudinal stress. This is called as longitudinal stress. It will get into two parts. It was like this. It was like this, and it gets into two halves. This is one half. This is one half. So this is the one reason it can fail, or this is the one direction it can fail. That means in longitudinal direction it can fail in this way. This part is clear. Please respond. Number one, failure is understood or not. It can fail in longitudinal direction. That means it will be fail either it will fail in two halves. If the pressure is applied more, the pressure this will fail in two way. This part is clear. Longitudinal way. Are you able to imagine? Okay. Another one is circumferential. That means another way is, suppose this is your cylinder. Circumferential. That means it will make one. This will be upper half. This will be two half. It will lead to this way. You will have one part over and another. There will be a downward part also into two halves. Just imagine you are cutting a cylinder into two equal halves. This is the upper part. This is the upper part, and this is the lower part. Okay, this is the upper part. This is the lower part. So so your cylinder can fail in two ways. Upper and it will divide into upper and lower part. Okay, that will be it is also called as hoop or circumferential stress. We'll discuss. So when the pressure exceeds in your vessels, it will get half. There will be two major ways to failure. One, it will be failed along the longitudinal, which is also called as longitudinal stress, and another is it will tries to break down the cylinder into two halves. There is one more stress, radial stress. Radial stress is negligible because we have considered This is the radial stress. This is the radial stress. This will be usually negligible because we have considered, see, radial stress is will acting along this thickness, and we have assumed that this thickness is terms of negligible. So this is the very minor stress, and we won't consider this stress for the analysis. So basically, in thin cylinders, there are two major stress. One is longitudinal stress, another is circumferential stress. We'll discuss it now. So basically, these three are the stresses applied on thin cylinders, and we design our pressure based on these three values. But radial stresses are usually negligible, so we design our thin cylinder basically for two stresses. One is circumferential stress, or you can also say hoop stress. Another one is longitudinal stress, and this is represented by sigma theta and sigma L. And these are the basic assumptions in the thin cylinders, that it is assumed that the stress are uniformly distributed throughout the thickness of the wall. That means if this is the cylinder, the stress is uniformly distributed. If here it is acting 3 kilonewton, here it is also will act as 3 kilonewton. So stress is uniformly distributed. Then, as the magnitude of radial stress is very small in thin cylinders, they are neglected while analyzing thin cylinders. So, as I discussed, your sigma radial stress is 0. So, let's start with circumferential stress. These stresses is directed along the tangent to the circumference of the cylinder. This stress is tensile in nature. Okay, this stress tends to increase the diameter. That means, just imagine you have a cylinder. You have a cylinder like this. It gets into two halves. So upper half will be like this, and lower half will be like this. Hope you are getting my point. So this circumferential stress means it will try to increase the diameter. See, earlier whatever be the diameter, now it is increasing the diameter. It is tensile in nature. We know tensile is in outward direction, so it is getting outward. So this is the one reason. This is the one way your cylinder will fail, which is circumferential stress. It will try to pull out the section into two equal halves. This is the one way of failure. So circumferentially, this is sigma T, and this sigma L is your longitudinal stress. Okay, these two are the major stress in thin cylinders, and this P is the internal pressure acting on the walls. Okay, this Pi, or you can take P, these are the internal pressure due to fluids acting on the wall. If you imagine like this, if this is your cylinder, your P is acting on this wall. Okay, this P is acting on this wall, internal pressure. So this Pi is acting on this wall. Same way, there will be one or downward part section. This is your thickness. This is the thickness of the cell. So circumferential stress, what do? It breaks the cylinder into two halves. This is the upper part. This is the lower part. Okay. So we have sigma theta, sigma L, sigma R. So let's see the derivation of sigma theta. So the bursting in the, so you always remember, see, when we stretch a rubber, when a force is applied on that, uh, we have a resisting force by the nature's god, or you can say, with always every structure, when you give a load, it has a tendency to resist that force. Okay, so let's start with, there will be one bursting force. Bursting force means the force we are actually applying, or the force it is getting, the force which this P is applying. Okay, the force this P is applying to uh, burst out. And we know pressure has a formula of force per unit area. And if you see, it is acting along the circumference. So this is the diameter of the section. This is the length of the section. So what will be the area? Your area will be D into L. Assume this circumference as a rectangle side. Assume this, because busting force is this one, right? The pressure this P is applying on the surface of the section. So assume this circumference as a rectangular section. So our diameter B is your D, length is your L. So what will be the area? D into L. D into L is our area, and P is your pressure is your this P. So what will be this force? This force will be your pressure into area, and our pressure is nothing but Pi. You can take Pi into area is dl. Got this point? So your busting force, that means the force due to this liquid is nothing but Pi into dl. That means this part. The bursting in the cylinder will take place if the force due to internal fluid pressure acting vertically upwards, acting vertically upwards and downwards becomes more than the resisting force due to the circumferential stress developed in the cylinder. So your total diametrical bursting force is P into projected area of the curved surface. As I discussed, area will be your D into L and your force is P. So bursting force is nothing but PdL. Understood? That suppose if I am taking the lower part, if I am taking the lower part, so assume this curved surface area, this is the diameter, right? This is the diameter, this is the length. So assume this curved surface area as a rectangle. So you will have a length L and diameter D. So area will be D into L. And we have pressure over this area, right? We have pressure over this area, which is P. The force tries to burst out. So pressure is nothing but force per unit area. So we need this bursting force. So force will be your pressure into area. Pressure into area. Pressure is nothing but this bursting force P into area is our D into L. This part is clear. Bursting force is clear. Please respond. Bursting force is clear. What about others? Type. Only one student are responding. What about others? Vijeshwata, Rupashri, others. Vincent. Okay. Okay. So this is a bursting force. So we know that. Whenever there is a force we are applying, there will be some resisting force. Okay. This is one. This is type it as equation number 1. So there will be a resisting force. When you apply a load, there will be by nature's God there will be a resisting force in every material. So resisting force in this structure, this is the force applied on this bursting force is applied on this circumference. But this is the thickness. This thickness. This is the contact area. It is trying to resist that force. It will try to resist that force. Just imagine you have a closed container and the pressure in the fluid is so much that it is trying to burst it out. But the structure is it is trying to resist that force. That it is trying to does not allow that it doesn't get burst out. So your this area, this the actually the contact area will try to resist that force. So it has thickness of T, and length L, and it has two strips. One 2. So area will be 2 into 2 times, because we have 2 T into L. This part is clear. Area of this strip. Force is applying in this area, but the resisting force will apply in this contact area. This thickness. This thickness will try to resist that force, and the pressure in this area is sigma H. And the area of this strip is L into T, and we have two strips, that's why 2LT. So now again, the resisting force due to circumferential stress will be this pressure into this area, 2LT. So we have equation number 2. Now we have to equate this, because this, if these two parts will be in equilibrium, then your structure, your you can take your cylindrical will be stable. If these two structures are not equal, if these two forces are not equal, then your cylinder will fail, right? So we have equated this part, and we got a formula of circumferential stress as PD by 2T. So this is an important formula. This part is clear. Hope this part is clear. I'm moving to another stress, which is longitudinal stress. This stress is directed along the length of the cylinder. This stress is also tensile in nature. This stress tends to increase the length. So that was the one way of failure of a cylinder, and we have to design by that stress, which is called as longitudinal circumferential stress. Next we have longitudinal stress. That means it will try to, suppose this is the one cylinder, load is applied in this direction, and it tries to make two half. It is getting two half. If you have suppose take an example of chocolate, you have a bar, 5 star. If you break into two parts, it will get some forces. You will see some lines and all, right? So in the same way, so these it will get into two equal half, and these are the forces you can see. So this is the longitudinal stress along the length. Why longitudinal? Because it is acting along the length. So total, so here also there will be bursting force on the cylinders. Now see, they have taken the area of the cylinder, pressure into area of the cylinder, pi by 4 d square. Pressure is P, and the area of the whole cylinder. Now the stress is acting along the area of the cylinder. So they have taken pi by 4 d square. Area of cross section where longitudinal stress is developed is pi d into T. It will act along this circumferential, right? Along this circumference. So they have taken the parameter pi into dt. This is the cross area, and the stress is sigma L. So sigma L pi dt. This is the overall bursting force we are getting due to liquid. This is the bursting force. Area into P. Pressure is equal to force per unit area. Force per unit area. We need bursting force. So bursting force is nothing but pressure into area. And area of the container is pi by 4 d square, and pressure is pressure of the liquid, which is P. So this is one equation. Now for the resisting force will act only on the this circumference of the cylinder. So it has, this is pi dte, and we have force pressure as sigma L. So force is sigma L pi dt. This is equation 2. This is equation 1. So obviously, to be stable, these two forces should be equal. So we have plot this two value, and we got longitudinal stresses sigma L PD by 4T. Okay. So see, we got sigma theta as PD by twice T, and longitudinal stress is PD by 4T. Now tell me, what is the relation between sigma theta hoop stress and longitudinal stress? What is the relation between two? And which one will be more? Answer. Please answer. Which one will be more? Which one will have, what is the relation? Quick. This is sigma theta is PD by 2T, and longitudinal stress is PD by 4T. So what is the relation between sigma theta and sigma L? And what is, see, somewhere in book or somewhere you'll get this theta as replaced by sigma H. No big issue. You can represent anything here. Somewhere you will find sigma theta, somewhere you will find sigma H. So don't get confused. It is the same. Now tell me relation. What will be the relation between these two values? Quick, quick. PD by 2T, circumferential stress, PD by 4T. What will be the relation? Response. What will be the relation between these two values? PD. Any answer? That is good that you have answered. Anyone? Respond, please. What will be the relation? You have sigma theta. You have sigma theta as PD by twice T. Very easy. And you have longitudinal stress as PD by 4T. What will be the relation? Arif, Arup, Atob, Atul, Bake, Bamang. What will be the relation? Bamang, what will be the relation? Nanu, half, PET. Good, Nanu, you tried. What about others? Bamang, tell me the relation. Ivan, Jojo, Ishan. What happened? Nisha, Madhusmita, Motyur. Are you all present? Or just attended, just joined the class? Okay, this is the interaction class. Otherwise, I could give you the simply record. I'm taking the live class. Reply, reply. Okay, see. Good, Omit. Good, replied. Okay. So, see. This sigma theta is PD by 2T and this longitudinal is PD by 4T. Okay. In sigma theta, PD by twice T. If I multiply it by 2 and divide by 2, will it affect anything? Nothing, right? I'm multiplying by 2, dividing by 2 also. I can write this one as PD by 4T into 2. Yes. So what is PD by 4T? It is nothing but sigma L. So sigma theta equals to sigma L into 2. I can write this way. So your sigma theta, that means your root stress is twice times of sigma L. Right? Your sigma theta is twice times of sigma L. That means your sigma theta will be larger value. It will be the major value comparison to sigma L. And it is how much major? It is twice times of sigma L. Suppose in reverse way I need to, in reverse way let's discuss in reverse way. So I'm telling you that sigma theta is a twice of sigma L. Is it correct or not? So twice into sigma L is how much? PD by 4T. 2 cancel. 2 will be left. So it will be PD by twice theta, which is sigma theta. So this relation is equal. This relation is correct. Yes or no? This relation is correct. That sigma theta is twice into sigma L. This part is clear. Your sigma theta is twice of. Okay. Uh, do one thing. You write your roll number. All of you write your roll number. I'll let's see some numericals also. Till then, let me find some numericals. What happened, Tucker? You have raised your hand. Any issue? And those who have not wrote their roll number, please write your roll number in front of your name. Jojo, write your roll number in front of your name. Ruposhri, write your roll number. Richa, write your roll number in front of your name next time you join. Hope everyone wrote their roll number. Okay. Let's see this numerical. My screen is visible. Screen is visible. Please respond. Okay. See, they have given a thin cylinder, 60 mm internal diameter, a thin cylinder, 60 mm internal diameter, 20 to 25 mm long, and wall thickness is given to you. And internal pressure is also given to you. And these two values we'll need later on, we'll discuss. But just see, they've simply asked to find the hoop stress. Hoop stress is nothing but circumferential stress. So they have used every value is given to you. P is given to you, which is 6 millimeter per meter square. D is given to you. You just have to apply the formula PD by 2T and get the value of hoop stress. In the second part, same, they have asked you to find out the longitudinal stress. So longitudinal stress is PD by 4T. So if you use PD by 4T, like or if you put all the values, you'll get the answer. So these are the easy questions, right? These are the easy questions. Simply you have to find out these values, nothing more than that. It is easy. Let me find another some numericals based on these two values. Okay, yes, got it. I'm sharing my screen once again. Is the screen is visible? Please respond.
My screen is not.
Okay, screen is not visible now. 13 example 13.1, a cylindrical boiler is 2.5 meters. Visible?
Yes, ma'am. Now it's visible.
Okay, okay, thank you. So, see, you have a question. A cylindrical boiler is 2.5 meter in diameter. The diameter is given to you. Thickness is given to you 20 meter mm. And internal pressure is given to you. See, all are in mm. So that you convert the diameter at first half itself, and they have asked you find here they have not asked you to find out the hoop stress or longitudinal stress. They simply ask find the stresses in the cell. So we know the two major stresses is longitudinal stress and hoop stress. So put the values in the formula, you get this answer. Okay, this one was easy. Now see this one. They've asked you a thin cylinder vessel 2 meter in diameter, 4 meter in length, diameter is given, length is given, contains a particular gas at a pressure, P is also given to you. They have asked if the permissible tensile stress of the material of the shell is T. Permissible means that is your design. That means that cylinder can carry this much load only. Okay, so find the minimum thickness required. Find the minimum thickness required. So see, you have formula for sigma theta. You have formula for sigma theta as what was the formula? CD by twice T, right? And sigma L was CD by 4T. So you have been asked to find the minimum thickness. When this will be minimum? When this will be maximum? Right? Yes or no? So from sigma theta and sigma L, we got to know that sigma theta is more. Okay. And when the sigma theta is more, that we know sigma theta is more than sigma L. So we'll take this value to get the minimum thickness. If we take this value, we won't get the minimum thickness. Okay, they've asked, see, sigma theta is inversely proportional to T. So when this will be more, this T will be less, right? So we'll take this value. So T is given to you, D is given to you, 2 is given to you, T you have to find and you have equate with 150. You can ask me, ma'am, why you have not used CD by 40. You could have used this value, but what I'm saying that you need to find minimum thickness as required minimum thickness. So when this will be minimum, when your this value will be more. And comparing to sigma theta and sigma L, sigma theta is more. We have discussed recently that your sigma theta is always greater than sigma L by twice, right? So that's why I have taken, when this value will be more, the thickness will be automatically less because inversely proportional. That's why I've taken this formula. So put the values, you will get TS 11 mm. Okay. So that's it for today. For this class.